Don't scroll. Not yet. Because what you're about to witness challenges something we've believed for decades. Mars. A planet described as barren, cold, geologically exhausted. A red wasteland beneath a thin, fading atmosphere. That's the story we were given. But look again. Some formations don't fit the narrative. Certain structures interrupt the randomness. Edges that appear unusually defined. Surfaces that seem almost aligned. Patterns that don't immediately dissolve into chaos. Mars should be ruled by erosion, by impact scars, by billions of years of disorder. And yet, in places, we see something that feels different. Not smooth, not accidental, structured. Our minds are trained to recognize symmetry, to detect intention, to see meaning in shape. So when geometry appears where only randomness is expected, it forces a question. Are we witnessing rare geological precision, or something that once had purpose? Because if this is natural, then nature on Mars operates with an artistry we are only beginning to understand. And if it's more than that, then the real mystery isn't the shape of the rocks. It's the history buried beneath them. Look carefully, not with assumptions, not with conclusions, but with curiosity. Because Mars does not reveal its secrets easily. And sometimes, the greatest discoveries begin with a simple pause and a second look. If questions like these pull you deeper into the unknown, subscribe to All About Mars Surface. Share this video with someone who refuses to accept easy answers. And tell me in the comments, what do you see? Let's explore the red planet together. Even now, Mars continues to change in quiet ways. Thin clouds drift across its sky. Dust devils rise and fade within minutes. Seasonal carbon dioxide frost spreads across the poles and then disappears, altering atmospheric pressure across the entire planet. The surface may look frozen in time, yet the climate still breathes in slow cycles. Mars is silent, but it is not static. Understanding the planet requires looking beyond its surface. The rocks, minerals, and layered terrains preserve a record of environmental shifts that shaped the red world over billions of years. Each deposit, each fracture, each sedimentary layer represents a different phase in Mars's transformation. The planet we see today is only the final chapter. Long before it became cold and dry, Mars possessed a thicker atmosphere. Evidence suggests that rivers carved valleys, lakes filled craters, and groundwater circulated beneath volcanic plains. This early period was defined by stability, temperatures high enough to allow liquid water, pressure sufficient to prevent rapid evaporation. But stability did not last. Over time, Mars began to lose its atmosphere. Without a strong global magnetic field, solar wind gradually stripped away lighter gases. As pressure declined, surface water became unstable. Lakes evaporated. Rivers slowed. Ice began to dominate the hydrological cycle. Water did not vanish. It retreated. Welcome to All About Mars Surface. In this episode, we move deeper than ever before into the internal systems that shaped Mars from within. This chapter explores the buried ice, hidden aquifers, mineral transformations, and geological forces that continue to redefine our understanding of the red planet. Mars appears dry from orbit. Vast plains of oxidized dust stretch beyond the horizon. Impact craters dominate the landscape. Yet beneath this thin crust lies a different story, one written in frozen reservoirs, chemical alterations, and structural collapse. Subsurface ice is one of the most significant discoveries in modern planetary science. Radar instruments orbiting Mars transmit radio waves into the ground and measure how signals reflect back. Variations in signal strength reveal differences in density and composition. Ice produces distinct reflections compared to solid basalt. These measurements uncovered extensive ice deposits across mid-latitude regions. In some locations, the ice is remarkably shallow, protected by only a thin insulating layer of soil. This overlying material shields it from direct sunlight and slows sublimation. Beneath the dust, the ice remains stable over long periods. Certain scarps expose bright layers along steep slopes. These exposures reveal nearly pure water ice, extending downward for meters. The layers suggest accumulation during earlier climate cycles when Mars tilted at different angles. Mars does not maintain a fixed axial tilt. Over millions of years, its obliquity shifts dramatically. When the tilt increases, sunlight redistributes differently across the surface. Ice migrates from poles toward lower latitudes. When the tilt decreases, ice retreats again. These orbital variations drive long-term climate patterns. The polar caps preserve the clearest climate record. Layer upon layer of ice and dust accumulated over time. Each layer represents a different atmospheric condition, changes in temperature, dust storms, and seasonal cycles. By analyzing these layers, scientists reconstruct ancient climates much like reading tree rings on Earth. Beyond surface ice, mineralogical evidence reveals extensive interaction between water and rock. Clay minerals form when basalt reacts with water under relatively neutral conditions. Their presence indicates long-lasting water stability. Sulfates, in contrast, form under more acidic, evaporative environments. Their widespread distribution marks a shift toward drying conditions. These minerals do not form randomly. They require specific temperatures, chemical balances, and durations of exposure. In many regions, hydrated silica deposits suggest hydrothermal processes, water heated by volcanic activity circulating through fractures. Such systems provide chemical energy gradients capable of supporting microbial ecosystems. On Earth, similar hydrothermal environments host life independent of sunlight. Volcanic provinces on Mars reveal additional complexity. Heat from rising magma could have melted surrounding ice, generating temporary subsurface lakes. As these bodies refroze, they may have fractured overlying terrain, producing chaotic landscapes. Large outflow channels cut across the surface, carved by catastrophic floods. These floods likely originated from pressurized groundwater reservoirs that breached the surface. The release would have been sudden and immense, reshaping entire regions within days or weeks. Such events suggest that groundwater remained active even after surface conditions deteriorated. Deep beneath the crust, pressure increases with depth. Combined with geothermal heat, this pressure may allow liquid brines to persist in isolated pockets. Salts lower the freezing point of water, enabling solutions to remain liquid under sub-zero temperatures. Certain dark streaks observed on steep slopes appear seasonally and fade over time. While their exact origin remains debated, some hypotheses involve transient briny flows destabilizing surface material. Even if no liquid water reaches the surface today, chemical traces indicate that subsurface mobility once played a major role. Mars's crust is fractured from billions of years of impacts and tectonic stresses. These fractures provided pathways for groundwater movement. As water flowed through porous rock, it deposited minerals and veins and altered surrounding material. Over time, structural weakening may have caused collapse features, pits, troughs, and subsidence zones marking areas where ice melted or groundwater drained away. The disappearance of water reshaped not only the climate but the internal mechanics of the planet. As the atmosphere thinned, surface temperatures dropped further. Without sufficient greenhouse gases, liquid stability windows narrowed. Ice became the dominant form of water storage. Sublimation replaced evaporation. The hydrological cycle slowed dramatically, yet Mars never became entirely inactive. Dust storms periodically envelop the planet. These storms redistribute fine particles globally, altering surface albedo and influencing temperature absorption. Atmospheric circulation remains dynamic despite its thinness. Carbon dioxide continues to cycle seasonally between poles and atmosphere. During winter, CO2 freezes onto polar caps. In spring, it sublimates back into the air, causing measurable pressure fluctuations. This seasonal breathing affects wind patterns and surface erosion. Understanding subsurface water is critical for future exploration. Buried ice represents a potential resource for sustained human presence. Extracted water could provide drinking supplies, oxygen production, and fuel components through electrolysis. Locating stable, accessible deposits remains a priority for mission planning. Subsurface environments also offer protection. Radiation levels on the Martian surface are high due to the thin atmosphere and lack of magnetic shielding. Mars is quiet, yet beneath its surface lies evidence of motion, energy, and adaptation. The story is not finished. All About Mars Space will continue tracing these hidden systems, examining how time reshapes planets and how even a silent world can hold a dynamic past beneath layers of dust and stone. Mars is not just a surface, it is a depth, and that depth is where its greatest secrets remain. Thanks for watching. All About Mars' surface will continue following these changes, exploring how time reshapes planets and how Mars preserves its history in dust, ice, and stone. Share your thoughts in the comments. Like this video, subscribe to All About Mars' surface,